Thank you again to the NSTF for inviting me to share some thoughts. In particular, they're thoughts that are quite close to my heart in terms of the research that we've been active in terms of myself and the team around me. And in particular, a lot of that relates to overall goals of trying to unlock our blue economy. But, you know, when you hear this coming from a geologist, obviously you have a strange perception in terms of what it is that's going to be unlocked and what sort of environmental damages are going to occur. And I'd hopefully try in this presentation to alleviate those fears and to try and paint a picture of how important marine geoscience is as a decision-making tool, not just for geology and mining, but for all aspects across marine sciences, not just in South Africa, but around the world. So to start with geoscience, what is it? So when I refer to geoscience here, I'm actually just really referring to marine geoscience, so the geology of the seafloor. And, you know, it's amazing how many people get you confused with marine biologists and, oh, dolphins and whales, that's cool. Whereas in actuality, you know, we're obviously more interested in what sits on the surface of the ocean, on the ocean bed, and what lies beneath that. So geoscience, the first thing you think of, oh dear, resource extraction. Oh yeah, massive environmental issues, etc., etc. And I think that that is somewhat narrow-minded in the way in which we are viewing geosciences as a whole. And we need to look at this from a far more holistic perspective, which is that we have basically a triangle. And on that triangle, we have resource identification and forward planning. We have resource extraction and management, and then we have natural environmental management. And the first thing that happens here, I'm just going to minimize this if you guys don't mind, is that everybody leaps to these conclusions. The conclusions are such that it's oil and gas. So let me move my cursor across onto the second monitor here. Again, asking for miracles. Oil and gas, the term seismic blasting, which is prevalent in our society, following on from the Shell debacle on the Wild Coast, oil extraction, and of course, strong emotions associated with this in terms of natural environmental management. So this is something that most people see when you say, oh, we're going to unlock the blue economy of South Africa from a geological perspective. Whereas, and I'd hope to be able to convince people otherwise, we look at different aspects, not just to do with resource management from an economic perspective, or when I say economic, I mean actual mineral perspective, but for other things. So we're looking now in terms of sustainable fisheries, sustainable energy, resource extraction and management that's done with clear cognizance of the natural environment around it. And of course, all of this framed within the context of major changes to our coastlines that are going to be driven in the near future by climate change. So geoscience, I'd like to actually then follow that with, does geoscience save? And in many instances, I'd like to actually put this forward to the panelists and to those that are listening. Here's a nice picture of a coastline that is obviously going to be under threat in time. We could have all the resources and the best economies in the world, but if we look at our sustainable development goals and the goals of, say, the National Research Foundation or the DSI or DST, we look and we see that we are pushing for sustainable urban futures. A lot of our coastline is heavily urbanized. In particular, Africa uses its ports as one of the major ways in which we can produce trade and make money. And South Africa has the busiest ports in Africa. So these are all resources that need to be carefully managed in terms of an actual blue economy that sits and is properly contextualized in terms of changing climates. So how do climates change over time? How have they changed? And where do we sit within that? So really what we're trying to do is we're trying to look at a green economy of Southern Africa that's actually going to be focusing on blue resources. Pardon me. So let's start with some of the basics, and please do remind me if I'm straying into time territory here. Let's start with the basic idea of resource identification. And if you forgive the pun, I think here that the waters are particularly muddied. So what techniques are used, firstly, and what is a resource? And everybody goes straight for the jugular of geoscience when we start to hear about resources and the techniques. And here's a good example, sponsored by the Association of South African Scientists, the ASSAF, where this was put out as an emergency response to the crisis that was occurring with the 3D seismic that was planned offshore of the Wild Coast. Interestingly, this is what people's perceptions are, that this is all we do is we seismic blast the living daylights out of the seafloor, whereas in fact, we look at things from many different perspectives. And I know this is quite a wall of text. You'll be fine, I promise. I'm going to lead us through it quite carefully. Basically, marine geoscience relies on several techniques that are not just designed for proprietary oil and gas exploration, but actually really what we're interested in and what I think will unlock our economy better from the long run are the detailed and high-resolution seafloor mapping and inspections of the seafloor and the subsurface in high levels of detail. So this is what we're aiming to do. All of this is geophysical in nature on the whole, so that relies on sound wave transmissions over a variety of frequencies and levels, many of which actually are corresponding to levels that are shared within the ocean by other marine sciences that aren't necessarily perhaps regarded as dangerous or deleterious to the environment. So we use sound in terms of being able to image the seafloor, and the most common tools of this are what we refer to as echo sounders, and in particular multi-beam echo sounders. Those allow us to see the seabed, and I'll talk about this now. Sub-bottom profilers, and then these tools that we call side-scan sonars. And I'll talk about all of these so that you guys have an idea of at least what the data means when I show it to you later. So to start with, I stole this figure from the British Antarctic Survey. I'm not going to claim it's mine. But basically, the principles of echo sounding is that you beam or emit a sound pulse down to the seabed. You can know the time in which that takes to go down to the seabed and then be returned from the seabed back to your ship, to your measuring device. If you know the speed of sound in water, which we can measure very, very accurately now, you can start to paint a series of depths. This has a multiple number of echo sounder heads in one thing, thus it's called multi-beam. And as you can see here, we are essentially painting a carpet of soundings on the seafloor that allow us to see the seabed shape and its depth, and to some degree also its textural character in 3 dimensions and in extremely high levels of detail. So here's what we typically think of when we look at things such as oil and gas. This is a seismic reflection profile. It uses similar geophysical techniques in terms of sound propagation. So what this is instead of making a map like this on the seabed, we're looking now into the seabed in 2 dimensions with depth over here and distance over here on that. And all of those squiggles and wiggles ultimately reflect sound as a function of their characteristics. So changes in density between, say, bedrock, rock, sediment, clay, sand or clay, etc. And that produces all of those wiggles. If you notice over here, this scale here, this is exceptionally deep. So this is probably down here, it is about 3 or 4 kilometers deep. It's going right into the Earth's crust. We are not so much interested in that from my research group's perspective, and what I see as being promising for the way forward for us in a blue economy sense. If I show you in comparison the stuff that we do, this little thing up here, that's basically a line there that's maybe looking at 10 centimeters to 20 meters of penetration into the seafloor using much higher resolution techniques and higher frequencies. These frequencies typically don't tend to cause frenzies amongst dolphins and whales. I've seen many come to just see what's going on when you're surveying. But, in the many years I've done this, must be now nearly 18, I've never seen anything in distress. And we obviously have protocols in place to start these systems up and to make sure that we have no negative impacts on the environment around us. If we look at that in a slightly more zoomed in sense, over here we can see this is a little cross-section using sound. We can see bedrock, we can see sand. And that's really what's quite important here, because we can see the sand, we can see layers in the sand. Those layers have a story to tell. So we can drill those layers, we can look at their ages, but we can't drill them, we can't explore them unless we know where they are. So these 2 mapping techniques, firstly with the multi-beam, which makes a 3-dimensional picture, and then this, which makes a 4-dimensional picture, because you're adding onto the multi-beam the concept of time. We're looking deeper and deeper and deeper below the seafloor, and we're going back in ages to the prehistoric record. And that prehistoric record, as I'm going to discuss, is exceptionally important to us in South Africa, and it's something that is characteristically overlooked by almost all planning bodies. So this is a side-scan sonar map. It's awful from far, but it's very nice up close. So basically what this is this is taking sound, and instead of measuring the time it takes for the sound to return to your sound device, you measure the intensity of that sound. So it's akin to, say, throwing a tennis ball against a wall, and that wall is made of brick, and then throwing it against another wall next to it, and that wall is made of grass. The intensity to which that tennis ball will bounce back basically gives an indication of what that material is comprising. So we do that for the seabed, and it allows us to get extremely high resolutions of the seafloor. There's a multi-beam bathymetry image of the same area. We collected the data at the same time. You can see a lot of topographic change there from far, but when you zoom right in and you look at the side-scan sonar imagery, we can see extreme levels of detail. So these are basically potholes that have been cut into a rock platform. This is a ledge that can be shown here. So these are shadows that are formed by the system itself. So it's almost like shining a torch on the seafloor, but that torch is made of sound. And those, interestingly enough, are key habitats for something like the coelacanth. So, we wouldn't know that if we hadn't had these maps. We just fortuitously found all of these cool looking seafloor phenomena. If you look at it from the multi-beam bathymetry perspective, you don't see much there. So all of these tools work hand in hand. And really, if you're going to be an effective research institution that's going to focus on marine geoscience or anything to do with the seabed, you're going to need these tools. Unfortunately, these data, though critical for any form of seafloor use, are ultimately very scarce to come by. There's only really 2 platforms available in terms of competitive use for academic institutions or educational communities. Those are both run by the NRF and the South African Institute of Aquatic Biodiversity. And that is 2 multi-beam echo sounders. One is a more shallow water version, and one can go to about 1,000 meters water depth to visualize what's on the seabed. Basically, that's it. There's stuff that's housed with the Council for Geoscience that's for commercial purposes, rentals. The only other platform available is a complete suite of equipment, as discussed here, that's housed at UKZN. So that is the only institution in Africa that's actually operating that type of equipment. So if you look at it, there are a lot of institutions that do not have the equipment or access to it, and thus the training aspects of things are severely limited within Southern African waters, especially so outside of our borders. So then that's how we look for resources. And of course, we will sample the seabed physically. But what is a resource? So let's take this from the purely commercial perspective now. If we're going to look into blue exploration and we're going to look at mineral exploration, there are a number of mineral resources that we are involved with in terms of prospecting for. And of course, with that, we have a lot of research that spins off. But ultimately, South Africa is a haven for a variety of different offshore resources. How we balance those in terms of extractions, marine protected areas, and ocean conservation is something that needs to be discussed quite carefully. But the main ones that we have are heavy minerals, phosphates, diamonds. I won't touch on diamonds so much here, and because they, I think, are going into the toilet a little bit in terms of price with these synthetic diamonds. And of course, something that we refer to as rare earth elements. And those are critically important for us as a country moving forward if we want to keep the lights on. So let's just take, for example, the first one, heavy minerals. So if we look forward in time to a more industrialized Africa, which is undoubtedly going to happen, heavy mineral commodities are ultimately going to underpin the increased desire for steel production and construction. So we extract titanium from a lot of these minerals. Traditionally, we were the biggest titanium producers in the world. Our coastal mines on the east coast of South Africa were producing the largest quantities and still have, I think, some of the richest payloads in terms of heavy minerals, but that has slowly gone by the wayside due to political issues there. But if we were to just take, for example, the offshore environment, a random river. So here we go. This is down the south coast. So that is the Bashi River in the Transkei. I'm not sure if it is the Transkei or Ciskei. Apologize if I'm offending anybody. This is just one example, and this map looks great. It's a bunch of colors, and I remember this is what actually got me into really doing marine geology. I loved surfing, and then my mentor and benefactor, Peter Ramsey, for many years, showed me colorful maps, and well, I got excited about that. So what this is showing you magnetic anomalies. So another aspect that we look at when we do research offshore is we try and see what the magnetic anomalies of the seabed look like. Why? Well, one of the main things is that if you have minerals that are magnetic or ferrous, they are picked up quite clearly by a magnetometer. And what we're seeing here, these orange-yellow features, are very high magnetic anomalies that associate with either rocks that are filled with magnetic minerals. So, the typical rocks that we get sometimes along the coast here, but also with sediments. So if I zoom in there, here's a multi-beam bathymetry map that we made off a ski boat, mind you, because, why would we have a research vessel that can help us to do this? So this was made several years ago before all of the platforms that are now available were put in place. Off a ski boat in this area, it was treacherous. The main thing to take away from, I'm just trying to see my computer here, is this area really is just unconsolidated sediment. So there's nothing there. There's no rocks at the seabed. There's nothing along those sorts of lines. And if I were to look at that now in terms of magnetic anomalies, we can see that a lot of that sediment is basically strongly defined by very prominent magnetic anomalies. So what it looks like is there's really good potential for minerals in this area due to an association with a river, big river that's draining a hinterland that's filled with all of these good heavy minerals that are held up in rocks. Those get eroded and discharged to the coast. And here we have a depot center for this. So in no way am I saying that this should be a case where we should go and exploit this. Not at all. This is one of our most favorite places in the world. It's more so just an example of what's lying out there that we actually really don't know anything about. So we're almost in a way trying to unlock a blue economy, but our hands have been handcuffed, we are blindfolded, and we're trying to find the keys to our handcuffs first. So these are small bites out of just happenstance data that we've collected that go, ooh, that's an interesting aspect to that bit of seabed. Let's take something that's perhaps a little less unexpected. So this is offshore Richards Bay. So Richards Bay, well known, and you can actually see the mine over here for Richards Bay Minerals, owned by Rio Tinto. And obviously they've been mining there, the heavy mineral content. There's a big debacle about their mining on the eastern shores of Lake St. Lucia. Obviously that was stopped and for good reason. But, offshore here, very strong turbid waters. We can see there's a large lobe of sediment. So this is a bathymetry map with this big migrating wedge of sediment moving down the coast. This is what we refer to as a spit bar. So it's a large body of sediment that attaches and is driven by swell-directed currents. We call that longshore drift, and deposits sediment out. And there are many features like this along the east and south coasts of South Africa. So if we go to this old figure, made, by the way, in 1986, so before my wife was born. And if we look at this, you can see quite clearly a whole variety of these features have been identified. There's seminal work that was done by Berg Fleming, who was at UCT or at the CSIR at the time, since left our country. And he's identified these. What does it look like in terms of thickness? Well, these things are enormous. That's up to 20 or 30 meters thick in terms of sediment. Why is that important? Well, if I were to look at that again, we're sitting here with a substantial quantity of material that has a very high total heavy mineral content, according to magnetic surveys. If I look at a cross-section, again, one of these little baby seismic sections. So this is all work that we've been doing recently. This is very old magnetometer data, but we've mapped this shelf quite carefully now, just because it's of interest to us in terms of these unusual sediment bodies that are developing. So, we know these things exist, and we've known since the 1980s, but really this is the first attempt to engage with them any further. Scientifically, they're interesting, but also from an economic perspective, these things appear to be quite useful in terms of resource extraction. But again, we're basing our decisions on very, very old, outdated work. So what are the need to grow agricultural economies? And so I searched for bat guano, because obviously that's one of the major things that is going to help in terms of a growing populace and food security, etc., is going to be something like fertilizer. And fertilizer doesn't necessarily just result in cow poo or bat poo, but actually one of the main things is the extraction and identification of phosphorites. So here's another map, and I'm pretty sure that you guys won't be stunned to hear that this map too was made in 1970-something, 1978, I think it was. So this was produced in the heyday of South African marine geology. It's a map showing the distribution of carbonate apatite minerals, which are basically proxies for phosphates. And phosphates are the key ingredient in fertilizers. If you're going to try and grow extra crops, trying to get better food security sense, this is going to be something you need to explore for. And so this is part of a research project that we've been doing. We've been looking at the seabed down here. Unbeknownst to us, we knew that there were phosphates there because this guy Summerhays identified them many, many years ago. But if we zoom into this area and we have a look, we find a variety of really cool things on the seabed. So here's again some multi-beam bathymetry. We've got this big peak. This peak is etched with a whole lot of strange looking seafloor features. It goes across here. This is what we refer to as king clipper ridge. So this data I've only just really gotten collected, and I've only just began to process it, so it's still a little bit rough. But in association with king clipper ridge, we find a variety of these phosphorites, these big black boulder-like looking features. We cut them open. Quite interesting. We analyze them geochemically. We find that they have very high phosphate contents. So, you know, something that could realistically be used as a resource, could be extracted. But, and again, this is what's interesting, is until you map this, until you actually start to have an idea of what's sitting on the seabed, geoscience being basically the magnet that allows you to find all of the various needles in the haystack, we don't know what's going on down there in terms of both biological or geological factors. So since we started mapping this, and it was very crude at first, we found that there was this unusual ridge. It wasn't showing up in any of our other bathymetry data sets, the South African National Bathymetry Map. This ridge is key in terms of kingclip and their breeding. It creates a sound barrier in which they allow themselves to locate and to call for breeding. It's obviously key to our fisheries industry. And, you know, I don't think when we realize just how unique this is, I mean, this is all just phosphate. When that is that unique, it's not something that you should just go in there and start mining. If we didn't have an idea of what was there, with our modern techniques, we could have made a serious mistake. And you wonder how many mistakes have been made in the past because we don't have a full picture of what's sitting on the seafloor. So how do we keep South Africa candle-free? You know, I think I'm going to make a t-shirt that says, keep us candle-free, because we need energy. It's very clear that we're battling with our fossil fuel production and ability to maintain that. So everybody's going to start going green. That's the world over. So we're looking at things such as wind farms here. So a lot of marine geoscience focuses on siting those wind farms offshore. But it's not just so much siting them, is that we need particular materials in order to make this type of green energy work. And these materials are rare earth elements. So rare earth elements are typically used in the production of wind turbine, wind farms, etc., as well as solar panels. So above me now, I'm actually load shedding, but I've got a whole bunch of rare earth elements that are operating for me. And so I'm able to sit and talk to you on this basis. So that sand that you see in that hand there is what we refer to as monazite. So monazite is a resource-rich sand that can be extracted, and it occurs in conjunction with heavy minerals. So ilmenites and rutiles and those sorts of things that I showed you previously. So when we are exploring for those, we could also be looking for things such as monazite. But I can guarantee you we know almost nothing about the distribution and zonation of monazite along our continental shelves. Yet these are the main things that are mined from Sri Lanka, India, etc., and a very, very profitable business, both for green economy in terms of making sure that we have good, clean energy, as well as for boosting our economic development. So yes, back onto resource extraction and management. So everyone just goes oil. That's what geoscience must be about, or mining, get the diamonds or get the phosphates. But I think, you know, this is fairly large misunderstanding. And I think it's a misperception that heralds, in my opinion, a greater disconnection between marine geoscience geology, which I always consider to be the ugly step cousin to all of the other more established and better funded marine sciences in South Africa. So I think there's a misperception as to what we do and the uses that we have that can work synergistically between all of the various disciplines. Take, for example, here. So here we have a bedrock outcrop. This is a multi-beam image. You can see there's bedrock here, and this flat-looking stuff is basically sea floor. And this is north of the largest beach nourishment in the world, the town of Aranyamut. So this is an area where Namdeb Diamond Company are actively mining in the coastal zone. They do this by enlarging the beach, nourishing the beach, growing it out and mining behind. One of the major issues is that these bedrock outcrops are host to the West Coast rock lobster, which is critically, I think it's threatened or endangered, I'm not sure. But it's the kind of thing that if you start to impact those communities, especially in terms of the subsistence fishes, etc., in these areas, you become part of the problem. You are actually not unlocking any blue economy, you're unlocking your own economy. So one of the big things here that we've been working on is we've been trying to understand or establish what exactly these mining techniques are doing to the bedrock, because obviously we can't have that smothered and thus changing the habitat of these West Coast rock lobsters. So here's a map, and this is probably about, we've mapped this area a lot, but this is maybe 5 years worth of change from 2023 back to 2019. And we can see blue here shows positive accretion of the seabed. Whitish light blue shows basically no accretion or change, which is essentially what you want. There's a little bit of error involved, of course, with the equipment. And then red is going to show you seabed erosion. And we look over here, that's the exact picture. I'll flip backwards and forwards. It's looking pretty cool. You can see that there's very, very little accretion. So we're having no habitat smothering. And instead, we're having the usual scouring processes that we should be expecting that operate on the normal scale in terms of these rocky communities on such a wave-dominated coastline that is southern Namibia. So this is the kind of thing that has to inform decision-making, not just as to where to find resources and how to take them, but also to manage natural resources. So we can't unlock any form of economy, blue or otherwise, if we don't take that into account. So here's my part of the world, about 20 k's north of this area. This is Durban. Here's the Mgeni River, which flows out, the biggest river in the actual KZN province, I think, apart from the Tugela River. Might not be the biggest one. Anyway, so what we find here is, again, a really good case study. We find that in many instances, and we know this, organisms that live on the seabed or on bedrock are reliant on their seafloor or benthic habitat. So these are species that are oftentimes used as indicator species for unusual biology, and therefore an unusual habitat that is associated with that. So here's a good example of using geoscience. This is all the mapping that we've done over the years to look at the seafloor and the seafloor shape, etc. And this is the mapping that we've done inspecting the subsea floor. So using sub-bottom profiling, we've been able to extract what the river channels do in the area. And it just so happens to be that we find a series of communities living on the surface where these river channels are exposed that are continuing to live there, but are estuarine communities, almost unheard of. Estuarine communities associated with brackish water, this is extremely salty water, there they are living. A very, very unique environment, same environment that was used to help zone and delineate the marine protected area of the Utugela Banks MPA. So, you know, this is a good example. We found yet another example like this that probably should be preserved. If we go one step forward, something like cold water corals, that's what CWC denotes. Cold water corals are also exceptionally important. They're seen as a keystone species, not a keynote, in terms of rare, very sensitive environments. And some of the work that we did, again, just purely fortuitously, just was like, can we take the ship down and go and have a look at the head of this canyon offshore the Tugela MPA? And we found a whole bunch of what appeared to be suspected cold water corals. And we've got a big research program that's going out to go and sample them next year and obviously observe them. The thing about this is that these have been used as key species to delineate marine protected areas. This area was hotly contested in terms of oil and gas concerns as to whether or not it should be included within the marine protected area as is. It isn't. So we sit with a really strong basis for extending that marine protected area. When I say hotly contested, basically guys told us that we would be regretting things and our careers would be ruined if we were to put up a fight about this area. Now we have strong scientific basis in order to be able to make sure that it is preserved. So as we can see, habitat becomes exceptionally important, especially so for marine protected areas. And these are considered one of the major sustainable development goals in terms of ocean resource conservation, as well as production of money. So these are considered to generate millions of rands in revenue yearly. The more we can produce these, the safer we are in terms of resource balancing between the extraction of mineral resources. This is the last one. And again, I'm going back to Kingclip Ridge. I was very excited about this. So this is not the most well-processed data. I'm still, it takes some time, and it's just me and my two hands, unfortunately. But if I look at this, again, we can see all of these little pimples sitting on the seabed. Again, these are cold water corals. This is an area that might well be zoned, again, for oil and gas exploration. Exploration is one thing, but actual extraction is another. We don't know. But this, too, is, again, an area where you might have very strong basis for the zonation of an MPA. And if we look, we can see these transparent bulges that are sitting on top. This is a very high-resolution seismic reflection profile. And those little bulges are essentially, again, what we think are accumulations of cold water coral. So what drives me nuts, though, is this, I had to borrow time and resources from an American ship that was driving or basically sailing through our exclusive economic zone. Why? They had to do the mapping because our flagship research vessel, the Gullis 2, is not equipped with any form of standard geological oceanography tools. There's no real multi-beam echo sounder. There's a basic sub-bottom profiler, which I'm not 100% sure is in working condition. I've been trying to get that started up. And there's a Cora. And it just strikes me as absolute lunacy that you have to ask people to please collect data for you over things that are so economically and probably biologically sensitive as this environment. And so again, to emphasize it, UKZN, one discipline of one person leading that, the only people to have this equipment actually at hand in an academic or educational sense. And I think this is just a very sad reflection of a country that prioritizes marine science as part of one of its strategic development goals. So there we go. Sorry, I forgot those were there. So how do we go in terms of forward planning and forward planning for resilience? So these are the resources that we have. These are the things that we need to unlock. But how do we actually make sure that in planning for all of this, we take into context our resilience as people in terms of risk profiles for coastal areas and our coastal vulnerabilities? We live in an area where we actually have no context to risk. Why? Because we have no research program traditionally that has underpinned the risks of things such as sea level rise, storminess, etc. So what are these risks? So the two major ones are natural climate change and anthropogenic climate change. And I'm not going to worry too much. I'm going to conflate the two here because each is just as bad as the other in terms of man or a human that lives in the status quo. Within this, we find different issues that are going to start impinging on us. The big ones are sea level rise and shoreline evolution. So this is something that we are unlocking now in terms of understanding what's happened in the past, but trying to then use that as a window into the future. Likewise, how has storminess changed in relation to changing major atmospheric drivers, driven, of course, by climate change? And this climate change, what we're looking at is actually climate change that's natural. It's divorced from anthropogenic climate change, but we know that we are heading to that point as we warm. Likewise, two extreme weather events, which I'm probably not going to touch too much on here, like droughts or floods. We've also been looking into that. And then if we were to go perhaps tangentially to that, we also have the tectonic and astronomic wildcards of, say, things like tsunami, which is not necessarily a major concern in terms of our waters, just regards the generation of fairly large waves. Okay, so if we were to look at this, sorry, I'll go back here. The one thing to emphasize here is that with all of these threats, the emphasis is always on defense. We'll defend against it. But we have no idea what it is, what magnitude, what scale, what recurrence of these things are going to be affecting those defenses. And we are very much not pragmatic. So we will defend, we will try and nourish the beach, we'll build seawalls, etc., as opposed to taking the lessons from the past and looking towards the future in a pragmatic sense. So we've done a lot of work on this and a lot of fairly high-level work too in terms of looking at paleostorms, changes in terms of sea levels, so paleo sea levels, etc. All of these paint a picture of previous states of shorelines. So what were shorelines like in prehistoric times? And in prehistoric times that are analogous to what we can expect with warming climate. So we are taking a step back and we're looking at these going, well, that was a problem. We had massive storm deposits forming that were way larger than anything that has been recorded. So I took a ground penetrating radar system and a Cora, and I went into the richest properties, the De Beers estates in Durban, and you can see storm deposits that go right up to their doorstep, formed in paleostormy conditions during the Holocene. So, we're really actually quite risky in terms of how we've developed and where we go forward. Likewise, too, these things should be forming the basis of practice in terms of management. We model things as opposed to actually collecting proper data. The modeling is modeling. It's only as good as the data that are provided to set the model boundaries. And in South Africa's cases, almost all of this, so our setback lines, etc., ignore the underpinning geological data. So that being what's happened and also how that happens in relation to the underlying geology, which conditions everything. So again, we're just basically making decisions without a real strong basis for why we make the decision we make. So this is one of my favorite images, and I'm getting there, guys. I'm nearly done. This is a lot of the work that we've done has been looking at offshore environments, and in particular trying to understand shorelines. So those are shorelines that are paleo shorelines that are left on the shore. So this is basically a 60-meter shoreline, a rocky headland over here, a big crenulate bay that's been developed into it. It looks pretty much just like Jesser Point for those of you that have ever been to Sodwana Bay and gone diving there. But this is submerged offshore Richards Bay on the seabed. So at some point in time, the oceanographic processes, the sediment supply processes, the sea level processes were such to produce this. How has this now been left behind? So this is quite interesting, is that these things are being left behind mostly by large rises in sea level. Rises in sea level that we may be expecting when we have catastrophic collapsing of our ice sheets. I can't think of anything scarier. We can have coastal squeeze, where you squeeze the beaches up against bedrock and they disappear, or you can just have a whole net sail overstepping of our coastline as sea level rises up and over it, basically drowning it in near instantaneous geological time. That's quite frightening for us that react in terms of, century scales. This is the kind of thing that happens within a couple of centuries. So, extremely active and dynamic change that I don't think we could ever engineer our way out of. And a lot of this is not actually catered for within the coastal engineering modeling and equations. So lastly, storms. So storms are a big buzzword in terms of climate change. We know that climates are warming. That tends to warm the atmosphere. That gives us more energy to produce these big storms. And we've been looking recently at a series of storms and storm deposits that show fairly extreme inundation events. So these are sitting now, not necessarily in the marine realm, but in the coastal realm. So here's a big stack of rocks. We've been using a drone to do this. Sorry, I've lost my cursor. There we go. A drone to make these images, which is pretty cool. And in here, we find oyster horizons. The oyster horizons aren't in situ growth of oysters. These are horizons that all these oysters have just been mangled. Big, thick, meter and a half deposits of oysters, all aligned in the critical direction, filled with bits and pieces of rock. There's estuarine species of bivalves in here, which we are now dating. They're all sitting at the dating laboratory. These things point to a big storm surge that was sitting at roughly the storm surge itself, and the water was probably much higher than this, at about 5 to 6 meters above sea level. And the preliminary dates that are coming back point to these things being in the Holocene time period. So quite scary in that we are sitting waiting for such events to happen. Likewise, too, here we have another example of really interesting storm deposits. So again, we can sit and see these are all oysters. They're encapsulated with sand and other bits of gritty materials. There it is there. The top of that sits at about almost 1.9 meters above sea level. So you can imagine you had a big storm surge washing over this, probably for another couple of meters higher, transporting all of that along the base of that surge. And that essentially, again, is giving us a proper concrete bit of evidence as to what has happened in the past. And can we use that in terms of moving forward for planning? Yes, we can. How do we do it? We need dialogue between planners, and we need more people to be doing this. So to me, and I think this is my last point in terms of the main aspects to things, the most worrying aspect to me in terms of resilience is the diminishing of our beaches over time. So we wrote this paper and we said sandy beaches can survive sea level rise. And that is true. If you have an unlimited amount of sand and you've got nothing sitting behind that sand, you can have a beach going for the rest of eternity if you so choose. But we choose this. So, I mean, that's a great photograph. I'm sorry, again, I stole it off the internet, but amazing photograph. That's the Golden Mile in Durban. I spent many happy years there as a kid. And you can see quite clearly, we've got a whole series of obstructions that border the beach. This beach, as sea levels rise and as storms continue, is ultimately going to be nibbled away in a process we call coastal squeeze. It's going to pinch out against all of those buildings. The worst thing about this is that there's no sediment to naturally nourish these beaches. We are mining the living daylights out of our rivers for construction sands. So those which would normally nourish the beaches, they're not doing so. Basically, the option here is either defend the beach for future years as sea level rise and storminess increases, or abandon it. And obviously, you can't abandon that level of infrastructure. So the only way that we are going to be able to really work on this is to come all the way back to the work done in the 1970s and 80s. well-funded competitive programs in marine geoscience that help to identify massive accumulations of sand within the nearshore environments. That sand produces a really good quality resource for beach nourishments. However, at this scale, you cannot use the maps that were produced in the 1970s and 80s. They lack the current levels of detail and resolution that are required to address our needs. We have the equipment to some degree and partly the experience, but really, this all needs to be put together through governmental organizations and a religious set of maps done. Likewise, how they're doing within most other developed countries. So I like to think then, yes, geoscience hopefully does save. We see the blue economy of South Africa. We see how it's underpinned within all of that. And I'll ask where to from here. So as I said, I don't know why that's not, sorry, we're having a bit of a cutoff here. So the status quo is concerning to me because there's a clear importance of marine geoscience in Southern African planning. But there's a steady divestment in research that obviously needs to change. And I don't think it'll ever change when we're consistently mistaken for marine biologists. There's also a lack of equipment for suitable training and for research. How do we grow ourselves when you have one single unit in which students are being graduated from and which degrees are being conferred? And so this is a unit that has actual syllabus content in marine geology and marine geophysics, and that is UKZN. This is staffed by only one person, so that also needs to be broadened, and not at one institution, but at many institutions where we have active dialogue between ourselves and where we don't build silos and kingdoms, but we work all together in terms of achieving the sustainable development goals of a blue economy. Lastly, marine geoscience seems to be inadequately subscribed to, despite the fact that there are many allied marine science disciplines that would benefit from a synergistic relationship. So I looked at the Saatchi chairs, for example. There's 6 Saatchi chairs in marine or ocean science, which is shocking in a way compared to perhaps astronomy. But nonetheless, there's nothing to do in any of these with marine geoscience at face value. There's no linkages. They're not marine geoscience related chairs, despite the fact that every single one would benefit very much so by working closely with geoscientists to solve the issues that we've highlighted here. So in conclusion, I think, it's not doom and gloom. This award that was conferred by the NSTF is, again, I think, for me, one of the best things. It's a recognition of hard work in this environment and the dawning, I think, of a new age in terms of marine geoscience, where we will be contributing. This is starting to work out in terms of, we had guest editorials for some of the Geological Society of South Africa things, who likewise too don't know what marine geology is all about. And two, other awards that have been conferred or recognitions given to work in the African sector on marine geoscience and the importance of it. Because, and I state this quite clearly here, we've got to dedicate this award. So he's born now, don't worry. But we need prompt changes, and we need changes that are made interdisciplinarily and holistically for us to see the beaches and coasts of the world as I maybe did as a child. Whether that will be possible, I don't know. But I think that we're making our first big steps to that. So thank you to, of course, the NSTF for this invitation to present. Sorry, I'm 3 minutes, 40 seconds over. And of course, for the award. I think this is the kind of recognition that's needed in South Africa and the impetus that's required for the turnaround of my discipline, which is small, but I think hopefully convinced you guys that it's important, and for meaningful progress in unlocking our blue economy. Thank you.